Monday to Friday.
From 9 a.m.
This is Views and News with Clarence Ford.
Only on Cape Talk.
Welcome back. Views and News with me, Clarence, through till 12 on this Friday morning, 9:37 exactly. We welcome Dr. Chris Smith, the Naked Scientist.
Morning, Clarence.
Good to have you, Chris. We were sharing a little earlier, and this out of the New York Times, the details essentially that the first 2 weeks of July were also most likely, quote unquote, the Earth's warmest on human record for any time of the year, according to the EU's Copernicus Climate Change Service. And matters arising after that sharing is when will the thermometer melt? When can't human beings deal anymore? When is it game over, since we are in a season of testing highs and records?
Well, really, it comes down to what you're adapted to, doesn't it? In the sense that there are parts of the world where it's much, much hotter than Southern Europe is experiencing at the moment. And people are just fine, but that's because they prepare in advance and life proceeds at a different rate than normally people would expect to carry out their activities in those geographies. And that's the problem, that it's a state of preparedness that is or isn't there. And in the places that are experiencing temperatures of 50 at the moment, there's just not the preparedness, either in the people or in the infrastructure or what people expect to do with their day. In terms of whether this is going to carry on, well, it will, won't it? Because as we warm the planet, then we're going to see more extremes of temperature, because with global warming, there's more energy in the atmosphere. There are therefore more likely to be more intense storms. And on average, temperatures will be higher, and therefore extremes of temperature will be higher. And that means winters could get colder in some places, but summers will potentially get hotter in other places as well. So really, this is par for the course. But don't forget, we've always had extremes. And back in history, there are lots of records that have been set that still haven't been broken today for high temperatures in some parts of the world. This is because weather is a random process, and occasionally you will get a collision of all the right ingredients to produce real extremes, and that's what we're seeing over Southern Europe at the moment, with a high pressure which is clamping the weather in that particular geography and leading to temperatures becoming extremely high. In the UK, where it should be a nice warm summer, it's pretty cold at the moment because Europe's drawing away all the nice warm weather.
Okay, so that's an answer to your question, Megan. Thank you for that question. Let's go to Zuki in Big Bay. She's on the line. Zuki, shoot.
Morning, Clarence, and good morning, Dr. Chris. Okay, this might be a bit of a weird question, and I hope I can explain it properly. So I'll start by saying I know we're not supposed to stick cotton buds in our ears, but when you do, and you if you turn it right, there's a spot that you can hit that, let's say, it elicits eye-rolling sensations. Why? What's happening there? Why does this happen? And why is there that ability so deep in the ear?
Hi, Suki. Well, the anatomy of the ear is such that there are various nerves that run very close to the ear or across the inner part of the ear where you can reach with a cotton bud. And you're quite right, you shouldn't. If you ask an ENT surgeon about cotton buds, they will roll their eyes and they will shudder and say, no, never stick these things in your ears because they cause so many problems. Your ears are very good at cleaning themselves out. They do not need the assistance of a cotton bud, which is more likely to cause trauma and infection than not using it. But because there is a close approximation and association of various parts of the nervous system which control muscles of facial expression, eye movements, sensation to the tongue, and so on, which run through that part of your anatomy. In some people, if you rub in that area, you can activate some of these nerves. There's one nerve called Arnold's nerve, which is a branch of the vagus nerve, and some people, I think it's a few % of people, if they stick things in their ears and wiggle them round, it makes them want to cough. So this is sort of similar to what you're saying. So I suspect that what you're doing when you stick those cotton buds in is you are recruiting nerves that run close to where you're sticking the cotton bud. And when you apply pressure, you can activate nerves. Even though you're not stimulating the end of the nerve, you can activate them along their length. And this sends a barrage of inappropriate impulses along the nerve, leading to, in structures that will be controlled by that nerve, activity. In areas that detect sensations coming from a territory supplied by that nerve, the sensation of something happening in the area supplied by that nerve. So I suspect that's what's happening in you.
Then we have a question around the moon. Let's go there. How did the men who visited the moon make it back to Earth? What was the process they followed, leaving and returning safely?
Going there was relatively easy because getting off the Earth's surface, once you're a few minutes into your flight, then most of the dangerous part is behind you. They flew to the moon. They then had a lander, the lunar lander, which enabled them to safely get to the surface, which used thrusters to slow down the trajectory of the object that they were in until it was at a safe speed to land. The moon has no atmosphere, so you can't use a parachute, so you have to use physics, basically rocket engines that fire in exactly the opposite direction that you're moving in to oppose your movement and slow you down. They then settled down onto the lunar surface. They spent time there investigating, collecting samples. We've got 1/3 of a ton of rocks back on Earth now, which were collected by those Apollo missions from the lunar surface. To get home again, they got back into that capsule. The engines that had helped to slow them down on their descent are then fired up again and used to propel the craft away from the moon surface and up into the air. It's then guided onto the right trajectory to get it onto an earthbound course. And then you enter the Earth's atmosphere at the right gradient so that you're not coming in too fast, which would mean that you were going too quickly and accelerating too quickly with too much G-force that would liquidize your astronauts. So fast enough that you're coming home, but not too fast that you cause damage. And you then come skipping down through the Earth's atmosphere. They needed a heat shield in order to make sure that they didn't burn up, because when you have an object moving through a gas or a fluid like the Earth's atmosphere at really high speed, you get something called adiabatic heating. This is actually the same way that an engine works. When you compress a gas, you are basically doing work against the gas molecules, and if you do work against something, you're giving it energy. And if you give it energy, its temperature rises. So when you compress the gas in front of your descending capsule, it gets very, very hot. So they have a capsule that comes in, has the right shape to deflect the gas around the front of the heat of the object, and a heat shield. It nevertheless gets very, very hot. And it then comes down through the Earth's atmosphere, losing speed all the time because it is working against the atmosphere. And once it gets to a certain speed, you can deploy a parachute. Initially a small parachute that will apply drag and stability to your craft, and then you apply bigger parachutes that can grab hold of even very rarefied air and slow you down, and then as you get closer to the ground, bring you down at a nice sedate pace so that you can then either come down to the ground or in some cases into the sea. And then you have support craft or support teams there waiting to come and pop you out of your capsule and rescue you home. So that's how they did it. And it hasn't been beaten as a method yet, because no one's been back to the moon in more than 40 years, although that is about to change. And it's interesting that India have last week launched their own latest lunar mission, not with people, but with a lander, which is going to visit the south pole of the moon when it gets there soon. And it will trundle around on the south pole. That's of interest because there's ice there. NASA detected ice there, and another probe detected ice there previously. And this is where NASA want to go with their next moon mission. The attraction of ice is, of course, it's the source of water, and you can use that to drink. So if we have a lunar base established down there at the South Pole, that's what they'll be drinking.
Let's stay on the moon. Somebody keen to know what is on the dark side of the moon.
Well, the reason it's called the dark side is purely because it's beyond our knowledge, because we can't see it, but it certainly isn't dark, because the moon goes in a big circle around the Earth, always pointing its face towards us, the same face, the face with the man in the moon in it. And this is because the moon is tidally locked to the Earth. It takes about a month for the moon to go around the Earth in one orbit, and the moon turns one complete revolution on its axis in that same time, and this has the effect of always keeping the same face of the moon pointing towards the Earth. But that also means that at some points in its orbit, that other side of the moon that we never see is pointing directly at the sun. Therefore, it will be extremely bright and extremely hot, and definitely not dark. We call it dark just because we can't see it, so it's dark in terms of our knowledge. We have been there in the sense that we've flown round behind it with craft, and even manned missions have done that. So we've seen it, but we haven't walked on it in that respect. But that part of the moon's surface is interesting because it's completely different from the surface that faces us, and the contrast couldn't be more stark. Although there are craters on the moon's surface facing us, there are far more craters on the other side of the moon facing away from us, and there are various theories to explain why that is. The moon has been melted many times as it's been slammed into by huge impactors about 4 billion years ago, but the outer surface of the moon has a different story to tell than the one facing us inwards, and is therefore certainly ripe for study. And it's going to be something that, as we get more presence on the moon in the future, people are going to be looking at to try and learn more about the early history of the solar system, because the moon has not resurfaced itself like the Earth has with tectonics and volcanoes. So all of those impact craters are a timeline that can tell us about the moon's history, and therefore our own planet's history and the history of the solar system.
We have a voice note in. Let's take a listen to one of them, Joe.
Good morning, Dr. Smith. On the point of re-entry of space vehicles and so on, I've often wondered what would be required to have some of the major airlines equipped with parachutes that in the event of systems malfunction, engine malfunction, with 300-400 passengers on board, can be deployed and land safely. Is that possible at all? And has calculations been done to understand what size the parachute should be, etc.? Be interesting to know. Shabuddin Ottery.
Thank you, Shabuddin.
Interesting idea. I think first and foremost, one has to consider whether or not something's practical and whether it's needed. Now, the airline industry is so incredibly safe in terms of how many millions of passenger miles are flown every year versus how often something goes wrong, that it's not judged to be a worthwhile thing to do to try to have in place something along the lines of what's being described, because A, it would be very, very difficult from an engineering perspective to do, and B, there's no guarantee it would actually make things any safer. So you'd just be spending money and burning more fuel and having a false sense of reassurance, most probably. The difference between a lunar module coming in with 2 or 3 astronauts aboard and some metal is that that's very, very light in comparison to hundreds of tons of aircraft, which is travelling along, albeit more slowly. But you've got something travelling along with hundreds of people on board. It's a pressurised environment, which if it had a catastrophic failure necessitating the deployment of some kind of parachutes, then almost certainly would have depressurised. If it depressurised, then there's no guarantee that all of the people aboard would make it, in the sense that there's going to be very rarefied air, not much oxygen. It's going to be very cold very quickly, and whatever caused the capsule or the aircraft body to break apart would have presumably done quite a lot of damage to the people as well. So if you had something that catastrophic, would you gain much more by having a whole system of parachutes to bring the object down? And then where would it come down? If it came down over land, then it might do more damage to people if it hit people. Now, luckily, this doesn't happen very often. And that's going back to the point I was making earlier, that it's such a safe industry because of all the safeguards that are put in place, the enormous efforts of engineers to make sure that these things don't just work, but we know that they work hundreds of % better than we need them to work. So the rates of failure are very, very low. But I suppose in theory could be done to have a system of parachutes, but it would not be trivial to stop something weighing hundreds of tons, doing hundreds of kilometres an hour, and with hundreds of people on board, all of whom would need oxygen and to keep them warm enough while you brought them down to Earth from extremely great altitude in some cases. So I'm not sure that it would be practical, and for that reason it hasn't really been explored. I have been aboard one of the original Concords. Remember the supersonic jets that came out of service more than 20 years ago now, but they've got one of the test versions of that at a aircraft museum not far from where I live, one of the ones that was used to do all of the initial testing of what these aircraft would do, how they would perform and so on. So there are some passenger seats, but most of the aeroplane is full of monitoring equipment. But as I went up towards the cockpit, I noticed there was this very interesting chute in the floor. And I said to the chap I was there with, who used to fly them, I said, well, what on earth was that? And he said, when they first built these aircraft, they didn't know what was going to happen. And so they built in the safeguard of an escape hatch so that if anything did happen and the crew had to bail out, they could drop down this chute. But if you think about it, you've got something that would be flying along at 1,000 kilometers plus an hour, and the airstream, if you dropped out of this chute, even with a parachute, you would be slamming into air going past you at hugely high speed, and then possibly smacked into the aircraft body or other parts of the fuselage. There's no guarantee you'd make it anyway. He said it was there more for people's own kind of reassurance than actually for anything practical.
A message in that flows out of a conversation that we had yesterday about a series of murders that happened about 40 years ago. The question reads, "Hi, Dr. Smith. Yesterday, Clarence and his guest spoke about DNA. How long can DNA samples survive, and how is it best stored?" Solly with that question.
Well, the answer is, I think, by looking at the environment and looking at what we've read DNA from, you can answer the question that way. The Guinness Book of World Records for sequencing the oldest thing, at least until recently, was held by Eske Willeslav at the University of Cambridge, as he is now, originally from Copenhagen. And he had done, I think, a 750,000-year-old horse, which he got from a cave in Spain. I think we've got DNA samples going back even further than that now. So the answer is that DNA, in the right environment, can last a really long time. The usual place that scientists go for when trying to get a DNA sample is teeth, because teeth have got nerves and blood supply, and therefore they have structures inside the body of the tooth which contain cells that are viable and alive. And because teeth are very, very hard, they are a really good time capsule. So if you find some tooth, you can drill into it. You can usually find some less fragmented DNA in there, and you can then read the genetic sequence. That said, it's still very hard to do because, like anything with time, the effects of the environment, temperature changes, moisture changes, radiation in the environment, these all damage DNA and cause it's essentially a giant polymer, like a ball of wool, long strands, and eventually it does begin to fall apart and fragment. And so the challenge confronting DNA scientists is they've got to work out how to put all the pieces back together. So you imagine I come to you with a very valuable vase which has been smashed into 1 million pieces. You might be able to put it back together if there were 5 pieces, but when you get to 1 million pieces, it's much harder to find where all the fragments went originally. But that's the challenge that they're trying to overcome, and we're getting better at it.
Then we have a question about the Large Hadron Collider in Switzerland. Dr. Smith, please expand on the new data concerning the Higgs boson. Does it affect the Standard Model? Stephen with a higher grade question, I guess.
Hello, Stephen. Well, this was announced in 2012, where scientists said, we are pretty sure now, and then they were sure enough to give a Nobel Prize to Peter Higgs, that they had found the Higgs boson. What's that? Well, when scientists began to understand what the fabric of the universe is and what it's made of, and that there are particles, and those particles themselves are made of particles, because the word atom actually comes from Greek, which atomos, can't be cut, because Democritus and other ancient Greek thinkers envisaged the world as made of tiny particles that were indivisible. But atoms are divisible because atoms are made of subatomic particles. We know that inside atoms are protons and neutrons and electrons, and in fact the protons and neutrons are themselves made of even smaller particles called quarks. We can work out, therefore, and come up with theories as to how all this matter works and how things relate to each other, and this is the Standard Model. It's almost like a palette that an artist has colours to paint with, but they are the particles and the force carriers which make the particles and the structures and the relationships between those particles that make the rules of physics and therefore the universe work. But when scientists did that, they had a missing part of their puzzle, which is, well, we can explain a lot of things from all of this, but we can't explain why things actually have any mass. In other words, when I put atoms on the scales, they weigh something. The Standard Model can explain how they behave in many ways and how they relate to each other, but it can't explain why they weigh anything. And by slamming particles, in this case hadrons, protons, together at the Large Hadron Collider at a fraction just below the speed of light, so huge energies, you can make them fall apart, you can make new physics happen, which shows you, through those collisions, the structures and relationships of these things to each other, and enables you to test various theories, so that if there were some kind of other particle that gives things mass, you could prove its existence. And that's what they did at the Large Hadron Collider. They were able to show that through these relationships that this entity, dubbed the Higgs boson, exists, and it fills in the missing gap in this standard model of how the universe works. They've since had some downtime of the Large Hadron Collider, updated some things, increased the energies, so they can then begin to test other aspects of physics, and those are the experiments which are ongoing now.
And unfortunately, we've run out of time, and there's so very many questions in, and that's why it's important for you to get the questions in early. We'll keep some of them over for next week, Joe. I think so. It's time for news coming your way next.